Hello, everyone, and welcome. Space volcanoes. It ignites the imagination, evoking images of fiery and icy protrusions being jettisoned into a void we have yet to fathom. It is a hard indicator of how truly explosive our universe is. Please welcome this evening Dr. Caitlin Ahrens from NASA's Goddard Flight Center. Caitlin's research will be highlighting those forces underlying the volcanic activity as observed on several known planetary bodies. Please give Caitlin a very big welcome.
Thank you so much. Hi, everybody. Oh my goodness, this is so exciting. So can you hear me all right? Yeah. Cool. Okay. Fantastic. All right. So bang, boom, pop, fizz. All right. So we're going to talk about all sorts of different flavors of space volcanoes. And so whenever you hear the word volcano, if I were to ask you to get a piece of paper, grab a napkin or something and draw it would probably, maybe look something like this. This is my grand artistic skills here. So you would probably think of some sort of grand mountain of some sort, maybe very conical shape like that. Some sort of activity, right? So lots of fire and smoke, maybe some lava dripping out of it too. But we tend to think of volcanoes as just being hot and fiery and active and doom and spectacular all the way around. And that's not necessarily the point, though. So yes, there is always some sort of activity, or maybe it was in the past, and certainly in the present in some form, no. But volcanoes can take so many different shapes. So again, just very basic definition of a volcano. It's usually some sort of mountain that would have some sort of vent at the top of which something in the ground is going out onto the surface. In which case you would have lava, rock fragments, maybe even hot vapor and gas, just something extruding out. So a grand textbook example here is Mauna Loa. This is out in Hawaii. So you would have this big, beautiful vent, all this fiery activity, the beautiful lava flows that are floating down this mountain here. I mean, this is pretty much just textbook volcanism right here on Earth. But even Earth has several different kinds of volcanoes here. You can have pits as well, or even like mud volcanoes are a thing. Stratovolcanoes, or also called composite volcanoes. You can have shield volcanoes. The different kinds of activity as well. So as if any of you have experienced the Mount St. Helens eruption as well. So you had some sort of grand activity that just completely collapsed the side of that mountain as well. The cool part is that we see all of this in the solar system, but on completely different surfaces, somewhat mostly different materials, somewhat similar activities, but some of them not so much. So we use Earth as our template of what volcanoes would be in our minds and our thinking. And then as we look at volcanoes in the solar system, then it's like, okay, does this match with any of our volcanoes on Earth? And in what way? Does it look like a duck? Does it sound like a duck? But then it maybe it moves or meows. And then we have to be like, wait, hang on. What? Why? So that's the fun part about space volcanoes. So some really beautiful examples here. So on the left here is Mars, and on the right is Earth, with just collapsing of volcanic material. You can create some really cool calderas. You can have some really pretty lava fronts going on here. You could also have cute little volcanic domes and like clusters here. So again, the left is Mars, and then on the right is on Earth. So again, very, very many different flavors of volcanism going on here. And then their eruptions can be all completely different as well. So Plinians and Hawaiians, Strombolians, and Pelians, and so on and so forth. So all of these are a scale, right, on how much lava, how much material do you get out of the subsurface, how much gas is being released into the sky, how big are your rock fragments? Sometimes you can get like ash and like itty bitty pieces of dust and stuff to maybe like big cinder cone rock bombs that can just scatter the sky. So we have to take into effect on that as well in our outer solar or in our solar system in general, just how active and not just the shape as well. So there's two main levels of volcanism. And then we subcategorize everything from there, though. So the first one is effusive. So effusive is really quite interesting. So it's runny, it's watery. It's like it's having an allergy attack, right? It's a lava flowy. It's mostly shields. So how these work is you get some sort of material and it just builds up and builds up and builds up and builds up and builds up. And it's very smooth on top. It does look like a shield just laid down on the ground. And that's pretty much how it got its name, is as if gods had placed shields onto the earth. And that's pretty much how they got their name, was shield volcanoes. Whereas you got explosive volcanism. So now you have way more viscous material. It's very sticky. It's pyroclastic. So pyro meaning fiery, clastic meaning just rocky. You create this really interesting cement going on of the lava and it just spews out everywhere. And these would be our composite or strato volcanoes. So the really big, beautiful, conical mountain types going on there. So now for the moment that we've all been waiting for here is pretty picture time, right? So we're going to go through the solar system and just to show you just all the different kinds of volcanism we can have. And starting off with good old Mercury here. So Mercury does not have in the sense of volcanic mountains or anything like that, but you have these big, beautiful, smooth, crackly looking basins going on here. So what happens here is that Mercury is very soft inside. He may look tough on the outside, but he's actually a big softy on the inside. So what happens to poor Mercury is that as Mercury had been pinpricked over and over and over and over and over and over again, that inside, that very soft, maybe caramel center inside of Mercury just kind of bleeds out a little bit and fills these basins. And we do call these filled-in basins. Very original, I know. But that's essentially what's going on. So a lighter term that we also use to describe these we call them scabs, because once that gooey inside of lava has now filled in the basin, is now crystallized. It's not going to evaporate. It's not going to sink back inside or anything. Once it's on the surface, it's like, okay, I'm here. It crystallized and just chill. So this is considered volcanism in regards to Mercury. Now on to Venus. So Venus, the most volcanoes in our solar system that we can observe. So more than 1,000 volcanoes that we have detected so far. And the data for Venus is very rough, very, very rough. From Magellan is fantastic, don't get me wrong, but we can't pick up really small scale geology that much. Now, is it probably geologically dead? Maybe. There's still a lot of debate that we're probably not seeing super explosive, ooh, there goes another one, volcano on Venus, but there might be some fresh-ish volcanic flows on Venus. Now, when I say fresh in a geologic sense, we're all astronomers here. So the sense of time is very different. So geologically, when I say fresh, it's probably under 10 million years. That's still considered young. So 10 million years young for some of these lava flows, indeed, on Venus, or younger. That could be great. Maybe thousands of years. So that would be like baby lava flows on Venus. But what's fascinating is that 90% of these are basalt based. That's fantastic. That means that a lot of the minerals that we're dealing with on Venus are very similar to what we see in Hawaii and Iceland here on Earth. Hooray. The other issue that we have with Venus, though, is that the environment that these volcanoes are in are completely different. It rains sulfuric acid and it snows metal on Venus. So yeah, slightly different in terms of the environment of Venus, of which we see these volcanoes. And aren't they beautiful, ladies and gentlemen? Look at those volcanoes. Yeah, no, I'm kidding. This is the beautiful, luscious atmosphere of Venus. If we were to see an elevation map here and then color code it, so the darker blues and purples are the lower elevation, the very pink and white areas, and the red areas are very high elevation here. So all of this, you just see this huge belt, this big, beautiful belt here. Let's see if I can do my laser pointer. Aha. So this big, beautiful belt of just volcanoes and lava flows all over the place. So volcanoes on Venus aren't just shaped like big, beautiful mountains. Some of them are. But you also have pancakes and ticks, which sounds yummy and terrifying at the same time. So these are pancakes. These are pancake volcanoes on Venus. They're really adorable. So how they're formed are like little mini shields, except they're much more porous. They're very fluffy materials, lighter material, very slushy kind of deal. So they kind of puff up. Now, if the pancakes get too big, and I'm meaning you like did not skimp on the flour and butter with these things. So if the pancakes get way too big, it actually squishes down into the surface and it fractures the surface. And so bigger pancakes turn into ticks. So you got a pancake in the center here, and then what happens is all these fractures from around the pancake happen. So we call them ticks, is because it looks like little like creepy insect legs coming out of it. And then this is Matmans. So Matmans is considered the largest, relatively largest shield-ish volcano on Venus. So still a tiny volcano, but largest one on Venus nonetheless. So moon, yes, our fabulous moon. We have International Observe the Moon Night coming up. We've got the annular eclipse. We've got a solar eclipse. So let's just all celebrate the moon. And so we're going to further that in encouragement and excitement about the moon with lunar volcanism, which is a little bit about what I do at Goddard as well. So very kind of similar to Mercury in the sense of just very large lava plains. There's no vents per se, but I'll get to that here in a bit. But the very large mare, you wouldn't have a single vent. However, you can have lunar domes, and some of those domes do have small little vents and stuff, though. So it really depends upon what kind of volcanism you're looking at. If it's mare scale lava plains or cute itty bitty domes here. So Gruithuisen domes, and a lot of these are are confirmed through CCD imaging on ground-based observatories, which is cool. So Gruithuisen domes, there's three spectacular light minerals. So we're talking feldspars, nickel, aluminum, very shiny volcanic domes on the moon. So we're actually going to be sending a mission, hopefully a small rover to the Gruithuisen domes in the next few years, actually. So that's going to be exciting. I'm going to toot my own horn here and mention this big dome here. And then there's its vent. So this is the Fracastorius dome. So some colleagues and I have just recently published a paper on this really big dome. This is near Mare Nectaris, if you're wondering what part of the moon that is on. But yeah, nice, big, beautiful dome there. All righty. So Mars, the king of the volcanoes, even though Venus has the most amount of volcanoes, but Mars has the largest volcano in the entire solar system. This thing is a beast. So if we were to just kind of atmosphere correct and really, really like digitally enhance the surface of Mars, over here you would have Olympus Mons, and then our three what we would call like the three sisters of Olympus Mons here, though. So it's Asclepius, yeah, Pavinus, and why can't I remember the third one all of a sudden? That's not good. Anyways, so again, basaltic composition. So we actually go to Iceland and Hawaii a lot of the time to study the volcano systems there to get us a better idea as to what's going on here on Mars. What I mean by subsurface chambers here is that material needs to be housed somewhere. It's reservoirs of lava. How are they stored? How deep are they? How wide are they? What kind of pressure would they have had to spew up all that material and then form a volcano and then all the lava and so on? So all of these are still ongoing questions with not just Mars, but all sorts of volcanism in the solar system. But I want to take a little trip into some fun history with imaging Olympus Mons. It's quite spectacular. So Mariner 4, 6, 7, 8, 9. You got 3 flybys. You got 2 orbiters. These were the very first photographs of another planet. These were the first remote sisters, and every single one of them missed Olympus Mons, the largest volcano in the whole solar system. Every single one of them missed it. Now, to be fair, this was the data that we were dealing with as well. So, you know what? That's fine. I'll give them the benefit of the doubt on that one, though. You know, great photography on that one. So finally, Viking 1 and 2 in 1975, hooray. As we were landing, we finally got the first images of Olympus Mons. So this is not from Viking, but this is essentially the best shot we have of Olympus Mons. It's absolutely gorgeous. So it's a shield volcano as it looks. This is a giant pancake. The solar system's largest pancake right here. Now, a couple of things to notice is that what you're seeing is north is actually down and to the right. So this northern bit here is just a sheer cliff. So what happened there? Why did it just like chunk fall off? Is certainly a big question still. And also look at the middle here. It's not a perfect circle. And it looks like there's multiple circles going on here. Now, what we call this is called a nested caldera. Here's what it would look like from the top up here. So what's happening here is that Olympus Mons had erupted several times. And we've counted at least 8 separate holes. Now, there might have been more, and they've all been like just kind of buried on top of each other. But from what we can count, just from this nested caldera here, is that you would have just a single hole, and it would explode. Now, once all that material goes bye-bye, that hole would collapse and just go like, oh, sigh of relief. That's a caldera. Just sigh. Oh, hey, guess what? It's going to be building back up of materials, you again, and another sigh of relief, another collapse. And it would just do this over and over and over again. And we could see that in some of our other images and geologic mapping of these areas as well. This whole region here, oh, Arcia. Ah, okay, that's the one I was missing. This whole region here is called the Tharsis region. It's like this giant volcanic plate on Mars. It's just big bulgy area of volcanic activity. So you can have like little itty bitty smaller domes. That's a volcanic dome. That's a volcanic dome. That's Tabanus. All of these have different multiple holes as well. All the different lava flows. It's just absolutely gorgeous. Yeah, so here's that big old bulge right here. So this is an elevation map. That whole big thing is just volcanoes, 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 volcanoes. Gorgeous. So if we were to see a geologic map of Mars, this is the most updated map we have. This is from 2011. But what's spectacular here is that there's so much cool geology on Mars. Every single color that you see here is a different geology. It's a different structure, a different formation. It's so cool. So a lot of the pink and like magenta, rosy colors that you see here is volcanic on this map. So there's Olympus Mons over there. There's our three sisters over there. Over here is Elysium Mons, which is kind of the outside twin of Olympus. I just wanted to show you guys some just like really high res up close pictures of some of the lava textures that we see on Mars as well. These are very fascinating of all just just different textures, which means that they would all form differently. Some of them would have more gas. Some of them may have ice trapped in its lava as well, and it can affect the flow. It can affect the texture of these as well. So a lot of these are just like very up close lava images, and so the scale of these images is roughly I want to say this is like 2 or 3 kilometers across. This is how high res this image is. So I mean we're talking like centimeters per pixel resolution here. So I could have gone more in depth though, but I want you guys to see just the overall texture of some of these lava flows. It's just absolutely gorgeous. And I helped publish and author a few chapters in this recent book, So Mars, A Volcanic World. So that was fun. All right, so moving on. Ceres. I'm not going to stay too long on Ceres. Ceres is a dwarf planet / asteroid in the asteroid belt. So Ceres, you have Ahuna Mons, this cute, adorable, possibly volcanic dome on Ceres. We call it the Lonely Mountain is because it truly is the only mountain on Ceres. And so what's weird is like, why? Why is it the only mountain? So there's a few theories going on. My favorite unfortunate theory is that Ahuna had cousins that were probably all over the place, and then they all got destroyed by craters or collapsed, which is another possible thing too. Because what Ahuna is made out of is mostly salt, and salt is not exactly a very stable mineral in the solar system at all, or even just salt domes here on Earth with a lot of erosion and everything. They don't last that long. Now, granted, Ceres doesn't go through Earth-like erosion, but collapsing in on itself is a possibility. So good for it for surviving from either imminent doom of collisions from asteroids or that it hasn't collapsed on itself yet. It's still going strong. So there's still a lot of debate going on with just the the formation of this thing, but we would consider this to be like a salty, briny type of volcanism. All right, onward to the Jovian system. We're going to go to Io. So Io is a very sulfurous little moon. It looks disgusting, in my opinion. It looks like moldy cheese, but it certainly would be stinky. It's sulfur based. Now, sulfur, not only would it give it its beautiful, gorgeous complexion of yellow here, but it's also a very soft, squishy mineral. So because sulfur is a very soft mineral, even on Io, you're not going to get mountains. Oh, no. You're not going to get beautiful mountains or anything, no. You're going to get like geyser levels of volcanic activity. So it's just pits. All of these different little pock marks that you see on Io here are all volcanic, and they're all active. Io is probably one of the most active moons, also aside from Enceladus, though, but we have better tracking of Io. It's closer. So these are separate images taken nearly a decade apart, actually. So this is from the Galileo mission. So this is a big, beautiful geyser popping out. And then years later, when New Horizons arrived at Jupiter on its way to Pluto, it also caught some big, beautiful, actually a few plume activities going on here, though. So very active, very beautiful. Now let's look at these up close, shall we? Yeah. So this is what I'm meaning by just it's just full of calderas. So again, you get this giant hole of vapor and sulfur and sticky, gooey, geysery stuff. It explodes, very, very explosive, very, very strong explosions, and then it collapses on itself. It oozes and scabs. So back to scabbing here is that this would be considered just the lava drying in on itself. What a disgusting little bit. So besides Io and Venus and Mars and Mercury and the moon, that was all mostly rocky material, sulfury material, very hot, very active. Now let's go to the ice side of things. So cryovolcanism. Now you probably heard volcanism, and then it's like, no. Let's see. That's Spock in the ice here. But what I mean by cryovolcanism here is, how do you get something so simple as just H2O? Yeah, you got ice cubes in the freezer right now. How do you get something so simple and make mountains out of it? You make volcanoes out of it. You make glaciers out of it. Just as simple as H2O. And it's fascinating because it's not just H2O. You can also have different structures. You can have different kinds of materials that can make ice at very low temperatures out in the outer solar system here. So right now, there really is no clear definition of what cryovolcanism is, except cold, the cryo part. And volcanism in this sense is anything from the subsurface that goes surprise and out it pops out of the ground somehow, whether it's lava through a vent, through a geyser, maybe it just oozes out. Any of that can be volcanism. So we see this on Titan, on Triton, on Pluto. We're still making fun discoveries as to like where these things are. What are the materials then? If it's not just water, you can have methane, you can have nitrogen, you can have carbon dioxide, carbon monoxide. Titan is weird, and I'll get to Titan here in a bit. And then what do we define as cryolava? Something would be sticky and liquidy enough to ooze at such low temperatures here. So back in 2018, we did have a cryovolcanism workshop, and it was like a think tank. It was wonderful. It was like a 3-day conference, and we all just kind of holed up in a room, and we're like, okay, great, we're gonna define cryovolcanism. We did not. but that shouldn't come to any surprise to anybody there. If anything, we left that conference with even more questions than answers, which is great because it gave us more work to do. Hey, but what we were able to kind of figure out though is all the different ways that material can ooze its way up to the surface. So you can have convection, so similar to like conveyor belt style, or like a lava lamp, right? So you got material just kind of floating up and floating back down and floating up and floating back down, and I feel like I'm in a Tai Chi class all of a sudden. Sometimes you can have partial freezing, which can create cracking in the surface. You can have sometimes these icy bodies have oceans in the inside of them too. So there's a lot of slushy activity going on where the ocean is like pounding against the hard surface, and it's creating cracking or geysers, or what we'd have as like fracture propagation there. Exsolution, you don't really typically get, except there is a little bit of that on Titan. So exsolution is just a very, very fancy way of saying bubbles. So sometimes bubbles can happen. And we're possibly seeing that on Titan there. Nearly knocked over my camera. Oh dear. So here's Europa. So beautiful fractures all over the place, but not necessarily meaning that these are volcanic. It's a matter of two different things. One is these little domes that we see here. So these are little itty bitty salt domes, similar to the salt domes that we would even see on Earth as well. So they're just kind of pockmarked in clusters like this. Now, looking at its cousin in the Saturnian system would be Enceladus. So Enceladus, in the southern hemisphere, you got these big, beautiful, almost bluey looking colored stripes, and we call these the tiger stripes. The official geologic term for them are called sulci, but we're going to go with tiger stripes for tonight. So the tiger stripes here, these are very bizarre to try to describe though. But if we were to look at the heat signature of these, I mean, these things are hot. Now, when I mean hot, I deal with ice. I think anything above negative 300 Fahrenheit is warm to me. So in relative sense, warmth at these tiger stripes is just as warm as the Pacific Ocean on Earth. And that's fascinating, is that it's just as warm at those stripes. And so when Cassini was going around doing its orbit around Saturn and taking pictures of all these really beautiful moons, it was just coming up and a geyser exploded. And the Cassini team was just like, oh, this is a cool photo opportunity. And oh, wait, hang on, we're going into a geyser. What's going to happen? But it's an orbiter. You can't really slow it down. You don't really want to. But all systems firing, all the instruments came on. We flew through the geyser. And what Cassini did at the time was essentially sniff the geyser with its instruments. It sniffed it up real good. And we confirmed not only water with the geysers, but also salt. And come to find out, it also had the same salt content as our oceans here on Earth. So, woo, that's a win. That's an exciting thing to happen. So yes, geysers in this case are considered volcanism. Now, onward to Titan. Titan is by far, in my opinion, the weirdest moon in the solar system. There's debates of it being a captured planet, which I fully believe on that because it's the only moon that has like a big, thick, luscious atmosphere. It has its own weather. It has climate zones. It rains. There's beaches. There's lakes on there. It's absolutely gorgeous. It's also very, very cold. So we're again talking negative 300 some degrees Fahrenheit here. So very, very cold. You definitely don't want to go beachside vacation here, or unless you do, if you're that adventurous, then good luck to you. But if it's not cold, water is solid. Water is absolutely solid at this point. So what in the world could possibly be liquid to make liquid lakes and rain? It truly has its own cycle where you have clouds, it rains, it fills up the lakes and streams and rivers, and then it evaporates and it starts the cycle all over again. Well, the answer is methane. So methane acts just like water here. It acts just like the liquid. It's truly fascinating. So there are potential volcanoes, cryovolcanos on Titan. And so if anybody is a Lord of the Rings fan in the audience though, so this is let's see, this one's Mount Doom. And then just south of Mount Doom is Erebor, which is the Lonely Mountain. So hooray for you Lord of the Rings fans out there. But this is potentially a volcano, and then some of its lava, cryo lava just kind of spewing out there. So we're gonna skip past a lot of the, as you can tell, a lot of the Uranus system here, and we're gonna skip right over to Neptune. So this is Triton. So Triton is Pluto's cousin from the Kuiper Belt. It is a unfortunate captured Kuiper Belt object, though, but still very beautiful. Unfortunately, we don't have that many images of Triton when Voyager 2 swept by it in 1989. But what's beautiful here, though, is that you have these big basins here. This would have been the vent, and all of this is cryolava here. So there's these big, beautiful lava basins going on here, and all of these little dark streaks. Now, this puzzled us for quite some time until about, I want to say 2017, 2018, something like that. I mean, like decades later. And come to find out, it's like, oh, these are geysers. How about that? They're geysers. Now, why in the world are they dark colored like that? Is because nitrogen at really cold temperatures, and when trapped enough, once it pops out of a surface, it actually turns black for not so long of a time, but it turns black. We actually see this on Mars as well in much tiny scale. Nitrogen does the same thing on Mars when it's trapped after a while, and then there's maybe like a layer of frost. The frost thaws during Martian spring. Nitrogen pops out of the ground and it looks black. Just a little puff of little mini geysers on Mars, but these are much larger scale on Triton for Voyager to image those. And then Pluto, yay, Pluto. So Pluto imaged finally in 2015 by the New Horizons mission. Just absolutely spectacular images from here. So our big surprise that we had is that the very southern part, all the way down here, I say southern, in technicality, it's still southern hemisphere, even though North Pole is pointing down because of how angles work with Pluto, though. But for the sake of this, it's like, yep, here's the southern hemisphere. There's some volcanic stuff down there. Now, whether it's active or not, probably not, but also we don't know because this was a flyby. This was our one chance and a very quick take a bunch of pictures as quick as we can, and then we fly away. And we're probably not going to go back anytime soon. So this is the best we got. So whether these things are still active, more likely not, because we do have atmospheric data from ground-based telescopes. And so we see climate changes on Pluto, which is really cool all in itself. But volcanically, probably not. Or if it is, then it's like really small, or it's oozing, and then we're not going to get anything in the atmosphere whatsoever. But this is right Mons, and then this is the rim all the way down here. This is the rim of Picard Mons down there. But look at all this cool knobby texture going on here, though. This is all that cryo lava that I was talking about. Now, again, water is still very much solid at this point, and even methane is solid. It's still a very weak ice at these temperatures, but still solid. So what now can be oozy and viscous enough to make this kind of texture? What can be cryolava at Pluto? And so the answer is ammonia. So the same ammonia we have in cleaning products here on Earth, ammonia acts like an antifreeze. It acts just like an antifreeze. So it lowers the freezing point of a lot of ices on Pluto, and it intermixes it together, and it creates like a big old, what is it, like a big slurp. Just kind of a big 7-Eleven slushy machine going on in the inside of Pluto going on. It's fantastic. Now, there might be other evidence of other volcanic activity on Pluto way in the past. So we're talking millions and millions of years earlier, besides Reitmans and Picardmans. So this is not a crater. This may have been a caldera at one point. So like I said, a collapse of material, of that cryolava material. So we see a collapse there. And then Kaladzi is a lot of like water ice and ammonia going on here. And there's also a big collapse pit here as well. So this might have also been caldera. So Kaladzi, there's hopefully going to be a paper out soon about that. The other one has already been published. Now, what do we do about all these volcanoes? There's only so much we can study in the solar system. So, and only so many missions that we can fund. So Da Vinci, Veritas, unfortunately, is on a hiatus delay right now. But at least with Da Vinci going forward, we're going to learn a lot about the atmosphere. It's not specific to volcanism on Venus, but what it's going to tell us about the atmosphere. As it's dropping down, it's going to be an atmosphere probe. It's going to drop all the way down through the different layers of Venus. That can really help us out. Tell us about, like, is there any recent volcanism going on? What kind of cloud systems are we doing? And also, what's the sulfur content like going on here? Because sulfur is a big component of that volcanic systems going on. Now we got Europa Clipper. That's coming along really nicely. Hooray. Congratulations to JPL on that one. So Europa Clipper, again, not specific to volcanism per se, or at least the geysers, but understanding what's going on the inside of Europa, not just the outside and take all the pretty pictures at it once, but what is going on the inside? Is the ocean still, is there a motion to the ocean here, or is it partially frozen and it's not as slushy as we think it is? What's going on the inside here? Because we have seen geysers, but not as spectacular as its cousin Enceladus. And then we got Dragonfly. Dragonfly is going to be a really cool mission to Titan. Like I said, it's Saturn's largest moon. So Dragonfly is going to be this giant quadcopter drone that's going to bounce around the surface of Titan. Now, again, not specific to cryovolcanism, but it's going to have a chemistry lab in the stomach of this drone. And so learning about the chemistry of the surface, what kind of minerals are we dealing with on Titan? That can really help us out to understand how are these volcanoes being built, what's maybe in the subsurface of Titan. That can just help us out. Like, what kind of materials can these volcanoes be built up? So there's just so many different questions to still explore with all these different kind of volcanoes. And so, like, not just the activity. Why have so many different shapes? What's going on in the insides of a lot of these planets and asteroids and dwarf planets and satellites and moons and so on and so forth? What about the materials, the ice, the salt, the iron and magnesium, the hard rocky stuff to the very, very cold stuff, and the different kinds of lava that you can deal with? So what's the materials going on there, or the mechanisms, the processes. How is it getting up onto the surface? How is it exploding or oozing? It's just so many different kinds of volcanism out in the solar system, to be sure. So like I said, the Mars, a volcanic world is available, and also the newest Pluto textbook is also available. You can find it. Actually, it's nice and cheap on Amazon. The Pluto system after New Horizons, there's all the up-to-date geologic formations, maps, learning about the ice, the atmosphere, anything that we've learned from New Horizons is now in that textbook as well, which I have also co-authored a chapter on as well. But thank you all so much for inviting me tonight. I hope you all had fun learning about space volcanoes. It's a very, very fun topic, to be sure. So happy to answer any questions. Thank you.
Yeah, can you unshare?
Mhm.
Okay.
Unshare. So Dan Platt had a question.
Dan, do you have a question? Or a comment? Dan?
Yeah, please, let's see if I can bring up what I wanted to ask. Whoa, it keeps moving. Oh, there it is. It moved over to there. Ceres has a slurry of salty mud underneath. And what comes up tends to be a mix of salt water. Pressure is pretty low, so you don't get all kinds of exotic ices and things like that. But you'll get a lot of sublimation. It takes only a little while, I guess, whatever a while is, for the ice to sublimate, and you're left with the salt that you described. The thing that is getting my curiosity going is how long does the sublimation process last, and what is the lifetime of the icy features in the various bodies that you've been looking at? How does sublimation in that time scale affect the way these things look?
That's an excellent question. So we'll start with Ceres. So Ceres, you're correct. So you do have a lot of salt residue going on, and all that kind of fun, slushy, muddy stuff. However, we don't fully understand how the salt actually is ingrained itself into the regolith, how much ice is actually involved on Ceres as well. We don't have a good estimate for that. We do have quite a bit of data from the Dawn mission, to be sure, but how it was all mixed, what kind of ratios are we dealing with, we simply don't know. And it's not just sodium chloride either. There's different kinds of salt, just to make it even more interesting. So you can also have magnesium chlorides and bromides, lithium chlorides, I believe, might also be on the list as well. So hey, let's just have fun with this. Similar salts we also see on Mars, so that helps. So how we're going about this is that there are people in the world that are doing experiments, mixing these different kinds of ice and salts and regolith in different mixtures, and just to see what's going on. So whether they're looking at the spectral side of things, I believe there's a laboratory up in the UK that mixes all these different materials together and then bakes them, so looks at sublimation. Most of their work is toward Mars, but it can be applicable to Ceres. So their work is really cool because they do a lot of carbon dioxide, ice sublimation. How does that mess with the regolith and the ice? If you layer it, or maybe you squish it all together and then you sublimate it. And we're seeing all sorts of different stuff. So as stuff is sublimating, what's happening is the grains become unstable, the surface itself becomes unstable, and you either get like little pieces of collapsing going on. But if it's at an incline, say like a crater wall or a side of a mountain or something, and something sublimates, you can get a lot of really cool flow of material as well, or slumping in that regard, or mass wasting is a thing, is what it's called too, if there's a lot of ice content to make it very fluid. So there's all these different kinds of formations, and some of them aren't really volcanically related either. Some of them can be glacial related. So there were glaciers on Mars. I don't think that there would have been glaciers on Ceres though, but the process itself is still fun. It's still investigating in a laboratory setting. That's the fun part. So then sublimation in general, with a lot of the outer solar system stuff, again, that's extremely difficult to understand fully because we need more experiments done. This is extremely cold stuff. But the colder you are, the stronger a lot of these materials are too. So we need to understand the strength, the density, the grains, how they're all cemented together. So like water ice at Pluto is extremely strong. It's just as strong as volcanic rock here on Earth, which is mind-blowing. It's so cool. So what does that mean for the other ices, like methane and nitrogen and carbon monoxide on Pluto? Well, we know methane is slightly weaker due to its chemical bonds, but we don't really have a good idea as to nitrogen and carbon monoxide. We just haven't done the experiments, or at least not extensively. So there's still a lot of work that can be done to understand just the material science of it, like almost like the engineering of the ices. How are they built? In what ways do they interlock? And or not? Maybe they're layered. And then how does that affect sublimation, or how does that affect the land formations and everything? So many exciting questions to be sure. But yes, there's a lot of exciting work to do. So I hope that kind of answered your question.
Thank you. Beautiful.
Another question on Zoom from Al Padilla.
Yeah, hi. Can you hear me okay?
Yeah.
Yes.
Yeah, okay. So you have Pluto with an icy surface, and it's been there like geologic time. When the ice sublimates, where does it go? There's not much of an atmosphere. I mean, is the planet evaporating?
I actually, yes. So good intuition there. So Pluto does actually have a slightly thicker atmosphere than what we were expecting. So it has haze layers. So it's not as full and luscious as like Venus or Titan, or certainly Earth in that regard. But there's some cool haze layers going on. Now, what we're realizing is that big, beautiful bluish nitrogen, methane, hazy atmosphere, yeah, it's getting sloughed off very slowly, but it's disappearing. It's evaporating. So, yep. So that ice is slowly, but it's evaporating, going bye-bye. And so also with Pluto's inclination and tilt and its long orbit as well, all of that's going to affect like what summer is on Pluto versus the winter on Pluto. There's also latitude differences as well. There's a whole paper on just the I implore you, Google Scholar climate zones of Pluto. It's a really fantastic paper by Richard Benzel and Alyssa Earle, his grad student at the time. And so it's fantastic work to just look at just how different climate can change thermally different areas on Pluto.
Any questions in the room? Anybody?
Where did you get the shirt?
Oh, Larry wants to know where you got it from.
Online. Yeah. I love finding these online.
Oh, yeah, Mira has a question.
Mhm.
Hi, Dr. Ahrens. I'm a new member of this club. I'm sophomore in high school. I loved your presentation. I found all the different kinds of volcanoes fascinating, and I have a few questions regarding what you covered.
Mhm.
So, what is analyzing volcanoes useful for, and what can they tell us?
My best answer would be why not, and it's fun. So
Don't say that answer to Congress when you go for money.
I know, right? Please give me money because it's fun. And I need a job. So no, so what's cool is that I just how not only how are they all different, but think about the bigger picture here of just how did the planets and moons form way in the beginning? How are they all different? Why? Why and how did they all become so different with different levels of volcanism? How did all these different materials spread out through the solar system as well? So it's almost like you're looking from the inside out and outside in, which I know it can just like break your brain. But all that's also the cool part about collaborations. Like I like to look from the inside out. I like what's happening on the inside, all the oozy gooey cryo lava and stuff. That's my cup of tea. I don't care what happens on the outside. As soon as it leaves the outside, I don't care anymore. But there's people out there that would prefer the outside and they don't care about the oozy stuff. They're like, oh, once it escapes and geysers and dust and everything like that. That's so cool for collaboration then to go like, okay, there's so many different pieces to still do. It's just giant puzzles. But it still goes back to just the evolution of our solar system, just how varied it is. And that's just our own solar system. And imagine what exoplanet volcanology can be, which is a thing. So there are folks out there that study exoplanets and they look at the atmospheres of exoplanets to see if we can see any little detection of volcanic activity, whether it's geysers, sulfur is a big one, and see if there are also like exovolcanoes, which also sounds like a B-rated sci-fi film now that I said that out loud.
Okay, and Louise has a question? Or was that the same?
Yes, hi. Thank you for a very interesting lecture or talk. Really enjoyed it. But you mentioned that Titan could be a captured planet. Was it just whizzing by the solar system and captured, or was it one of the interior rocky planets? Or I mean, is there any other study or comment that it might, in fact, instead of just being somehow a moon way out there, very large, an actual planet?
Yeah, truly. Right now it's still just debates, it's theories. I'm just like, well, what happens if it came from this direction, and what happens if it missed the stop sign over here? So we think it would have been from the outer solar system, but how long ago? More likely not Kuiper Belt area, maybe a little bit toward Uranus, Neptune. But then how would it have been captured? Because it doesn't display any sort of retrograde type
Right.
tendencies either. It's just I think a lot of the theory comes about that why is it the only moon of Saturn, let alone of the whole solar system, that has an atmosphere, a weather system, lakes,
Yes.
dunes, so on. It's seasons, rainy seasons. It has monsoons. It can flood. That's another cool thing about Titan too, is that there's these little islands in the lakes of Titan, and they can flood. They can flood over those poor islands, but it's really cool. We have images of these islands getting flooded over and then reappear and disappear. It's so cool.
So
All the way out of Saturn.
it's really in motion then. I kind of living.
Yeah.
Oh,
Yeah, unfortunately, we're not going back, well, until Dragonfly, but Dragonfly is not going to be an orbiter or anything. It's just going to be a lander drone hopping about in only in one area. So we're not going to be anywhere near the lakes, unfortunately.
that's too bad. Well, all right. Well,
I know. Yeah, we need another orbiter to be sure, but it's not unfortunately on our priority list, according to Congress right now. So our priorities are elsewhere in the solar system,
Right.
according to Congress and the National Academy of Sciences.
Okay, so if there are no additional questions, I'd like to thank,
Sorry, I just have a few more questions.
I'm sorry.
All good, Mira. Hey, Mira, if you'd also like, feel free to also email me as well, and happy to also like catch up and chat about like space volcanism and just like planetary geology in general too.
Oh, sure. Yeah. I was just wondering, I just had a few quick questions. So
Mhm.
if you don't have
Yeah.
any time constraints, if I could just like address them now, or
Sure. Is that okay with the
Yeah,
room?
well, like we have another 5 minutes.
Okay, so we have another 5 minutes, but Mira, I'll also put in the chat my email address so that way you can email me just in case.
Okay, thank
But
you.
yeah, go ahead and shoot with a question.
So, as you mentioned earlier, it all boils down to like the start of the universe and like how all these different planets and moons formed. So you also mentioned that several planets and moons shared similarities with Earth, like similar water content, temperature, composition of the environment. Is like, what's the reason for such environmental similarity? Is it just luck, or is there like a deeper reason?
There might be a deeper reason. So this is a big question for Europa Clipper, which is the first of its kind to really understand the ocean of an ocean world. So there's this whole what we call a roadmap of NASA called the Ocean World Roadmap. I know, very original naming on that one. But these ocean worlds, again, how active are they? How big are these oceans? How salty in comparison with Earth here? The volume, also with size. But how are they formed, and what kind of core are we dealing with on the inside of these ocean worlds? Because to have a very warm ocean, you would need a warm core to keep it warm. And so we don't understand the cores of these things. We barely understand the core of our own Earth. So in that regard, Clipper is going to help a lot with that, to at least help spur on probably way more questions than we know what to do with ourselves. So we at least know the chemistry just by Cassini's luck of flying through a geyser, but that still created way more questions. Are all geysers like that? Probably not. We didn't fly through a geyser at Europa. We know that it's water detected by Hubble, but that's all we really know. We don't really know the activity on a lot of these moons as well, because we just simply don't have as much data, unless we were constantly watching it, but we can't. So there's only so much we can do, but also like the list of questions keeps growing with these ocean worlds though. So definitely look up ocean worlds, and you're gonna get into like a rabbit hole of stuff with ocean worlds.
That's fascinating. Thank you for mentioning that to me. Now I just want to pivot real quick to volcanoes now.
Mm-hmm.
So, I was wondering, as Mr. Platt said in the comments, there isn't significant pressure in Ceres' volcanoes. So what prompts this like cold mud salt slurry to erupt in the first place?
It's a very good question. mainly because we're still learning how mud volcanism works on Earth. You don't really need that much pressure. So what may have happened at some point is, one, Ceres used to be an ocean world. It's now what we would call a relict ocean world. So its ocean is just dead. It's dead. It's no longer slushy. It's all frozen over now. If anything, it's like a giant geode. It's just nothing's there anymore. It's no longer slush. So when it was a probably active, very, very salty, slushy ocean, it may have had the pressure at the time to make these domes. Now, if it is younger than that, again, we don't know age of these things very well. If they're younger than that, then another potential thing is you get like asteroid crashes that can shake up the ground and essentially like shift up material very violently. So that's a possibility as well. There's also fractures all over Ceres, so you can have like a little bit of tectonic stuff going on. So it might have been very slow. It might have been just a very slow squeezing of fractures to make all the material slowly build up, or is also from the ocean. so again, TBD, to be continued on that one. We need another mission to Ceres, but unfortunately, we're not looking to Ceres anytime soon either. If we could do a sample return for Ceres, that would be fantastic, but not really in the plans right now.
That's amazing. And do differently shaped volcanoes emit different substances, or does it depend on the environment or composition of the ground?
Yes. So all of the above. We're just going to circle that in, all of the above. So it really does depend upon your environment because it's feeding in, but then what's on the inside to feed out. So it's a really interesting cycle going on here, is that a lot of outside crap can come in and stir up stuff, but also if there's oceans, if there's salt, if there's ice, if there's metals on the inside already, and that's stirring it in, you know, what could pop out? Is it bubbles? Is it lava? Is it giant rocks of doom to spit out? All that's gonna depend upon how gunky it is on the inside, the structure of it. If it's a big mountain, there's a lot of time for that stuff to stick and explode. Whereas if it's just an itty bitty dome and an itty bitty vent, you're gonna get a lot more oozing as well. So the shape affects it, but the materials are the key. What's the building blocks of these? That's the key. But it's always the tricky part.
Thank you so much for answering my questions. I probably have more, so I'll be probably reaching out.
Yeah.
This is interesting.
That's all good. Thank you. So I put my email in the address, and Pat also has my address too, just in case if you miss it in the chat though. But again, thank you all so much for having me here
thank
this
you
evening.
so
I
much
hope
for a
everybody
wonderful evening.
has a fun evening.
Hopefully you'll come back again and give us an update. Okay.
That'll be fun. All right.
Good night. Bye-bye.
Good night.
Thank you.